Welcome back to Introduction to Data Science. So in this segment I want to talk about these 4 dimensions that I introduced last time, and I want to justify the first 3 of them. And we'll talk about this one next time. Okay, and by justify what I mean is I want to explain why I've positioned the needles the where at the locations I have for this course. Okay, so the first point here is this dimension of tools versus abstractions, and this may seem sort of obvious that we want to focus on fundamental concepts as opposed to specific tools, but I can appreciate that people that are taking this course and many other courses really want sort of hands-on experience, and we're definitely going to try to strike a balance, but let me try to motivate why I think it's important to sort of focus on this angle. And to do this, let me tell one particular story that you see happen sort of time and time again. So in this case, we're talking about sort of databases and what is currently going on in the NoSQL systems. All right, so before 2004, you had, the big 3 relational database vendors plus some open source solutions like MySQL and PostgreSQL. And then arguably a big event in 2004 was when Jeff Dean and his colleagues published this paper on MapReduce at Google. And if you haven't heard of MapReduce, we'll talk about it at length. And if you have, bear with me. So this was great. What this allowed you to do was process very, very large data sets, and it sort of rebooted the database feature set. So it really focused on just scale out parallelism, and that's it. None of the other features of databases. And this was exciting to a lot of people because they didn't have to sort of deal with the extra features that they didn't need in databases, nor pay the exorbitant license fees associated with databases. So this seemed like, boy, this is the right solution. Okay. And it took a few years, but a few years later you had an open source implementation of the ideas in this paper called Hadoop, led by some folks at Yahoo. Now, even in the same year, one of the earliest and most successful projects within the Hadoop ecosystem was this system called Pig. And what Pig essentially was a relational algebra programming environment for Hadoop. And if you haven't heard of relational algebra, don't worry, we'll talk about it. But let me convince you that you notice the word relational there. Relational algebra is the secret sauce within relational databases. And so a very early on project that was deemed necessary in the Hadoop community and was wildly successful was to have relational style programming on top of this non-relational system. Okay. Moreover, you had other competing projects like Dryad Link, Dryad and then Dryad Link, which is an interface to Dryad, which also provided a relational algebra-oriented programming environment for large scale-out parallel data processing applications. Then you had people literally put the language SQL on top of Hadoop. So instead of just the underlying formalism, it literally had the programming language you needed. Then a bit later you had indexing for Hadoop, which is another feature that databases have that we'll talk about. You had people talk about schemas and more sophisticated types of indexing, which is 2 other things that databases have. And then you now start to see transaction processing being a very very important topic in NoSQL systems. Is how to support concurrent access at very large scale transparently. And this slide is perhaps a little bit old. It's now 2013, of course, when at the time of this recording. And the Spanner system from Google is a important system to look at that we'll talk a little bit about later. Okay, so now this isn't to say that MapReduce was useless. We're going to talk about it at length, and for a very good reason. It actually has some pretty important permanent contributions, 3 of which I mentioned here. One is, it was the first system to really emphasize fault tolerance, and the idea here in a nutshell is that when you're working with 1,000 computers at one time for any length of time at all, a few minutes, a few hours, the odds of one of them failing in some way is extremely high. And so databases didn't typically have to worry about this because the assumption, first of all, they weren't running on thousands of computers at once, and second of all, they were sort of under the assumption that your queries would typically be pretty fast. Okay, and so fault tolerance during query processing, so you don't lose all the work you started on when you're running a query, was something that the Hadoop and the MapReduce paper really sort of emphasized and has now been sort of accepted by the larger community. The other notion, which is a little more subtle, is this idea of schema on read. And what I mean by that is, the way databases worked in the past and largely still work is, we design this thing called a schema, which is a particular structure for your data. And then your job is to fit your data into that schema. And until you do so, we don't really want to talk to you. You know, the database has nothing to offer you until you're able to sort of fit it into some sort of a schema. Okay. And the observation was that, well, look, a lot of data doesn't come pre-equipped with a schema. We don't have a schema just sort of lying around. We have to do something with it. You know, and it's huge. You know, it's many hundreds of terabytes or something. So what do? Well, you know, one answer is you can use these MapReduce-based systems, you know, Hadoop for this. But having to say that before you're allowed to touch your data, you must load it into a database, that was kind of a non-starter for a lot of applications. Okay, and then finally, you know, this idea of user-defined functions is something that all databases, or most databases, support. And it's the idea that you might want to do things outside of what you can do in a normal SQL query. You might want to write your own code and push it into the database. But the experience of having to sort of write and maintain and manage and use these things is not great. And that's why a lot of people put their logic inside the application as opposed to pushing it down into the database, where arguably it could do more good for reasons we'll talk about. Okay, and so I think, you know, MapReduce sort of argued that, look, you can give the Java programmers what they want, a Java programming environment, and let them write scalable systems without forcing them to kind of use this crazy user-defined function interface that databases offer. Okay. So fine. So what's my point over all this? Well, you know, if we focus too much on tools, what you would get is a snapshot in time of what tools are important, as opposed to seeing that some of these features around databases are, you know, they sort of ebb and flow in their popularity, but they're sort of a permanent they're a permanent value when you're reasoning about large-scale systems. Similarly, you know, you might lose track of what's actually novel and what's actually new in the midst of the conversation about sort of relational databases versus NoSQL systems. Okay, so I want to focus on these abstractions throughout the course whenever we can. Great. Now, okay, so fine, we're going to focus on the abstractions. What are the abstractions of data science? Well, it's not clear that people really know yet, and I'll give my case for this in the next slide. But you know, the reason why I don't think we really know yet is you see these words being used like data jujitsu and data wrangling and data munging, and this, you know, this is the real skill of data scientists, that they have to be able to wrangle data. Well, what does that mean? Okay, so my translation of this is we don't really know what we're talking about yet. But that said, there's probably a few candidates we can consider here. So maybe everything's a matrix and everything we want to do with data, it can be expressed in linear algebra. If you're a database person, maybe everything is a relation and everything you want to do is expressed in relational algebra. If you're more of an object-oriented programmer, everything's an object and we communicate between objects by sending messages back and forth through by calling methods. If you're more of a sysadmin type, then you know everything's a file and we write bash scripts to process it. And if you're an R programmer, then maybe everything's a data frame and we call functions in this library. And MATLAB, similarly, perhaps with MATLAB everything's an array or a matrix or a vector, I guess, in their parlance, and everything's a function on that. Okay. So I think of all these possibilities, there are two that stand out as likely candidates as fundamental abstractions for data science, and those are the first two here. And the reason is that we see these abstractions appear over and over again, independent of particular tools. Now, relations and relational algebra are closely associated with databases, but as I argued a few slides ago, and as we'll see throughout the course, you see this come up time and time again. Okay, and you even see it in, say, you know, object-oriented languages, and you see it in R and so on. Okay. So these are the two that we'll mainly focus on in this course. So now I want to motivate desktop scale versus cloud scale. And you know, the argument here for desktop scale is that, well, you know, data science is really about the functions and the statistics and the manipulation, the techniques. So therefore, we can sort of push large-scale data into a separate course or a separate category and really just focus on the math and the functions. And I think this is a bit of a mistake for a data science course. And the reason is that, you know, this is a fundamental limitation of a whole category of technologies, and R itself is included in that, although there's a lot of great work on how to sort of scale R up. But as you know, in its basic usage, what you do with R is you read a file, load the whole thing into main memory on one machine, and then call functions on that. And so if your data doesn't fit in main memory on one machine, you're kind of out of luck. Now, you can be clever and start to use indices to kind of limit the data that you need to access, and you can start to try to be parallel to take advantage of the fact that there's now 4 and 6 and 8 and 12 cores in your machine, in your computers you'll buy nowadays. But trying to be clever in doing that yourself overlooks the fact that a lot of these techniques are pretty well understood and already implemented in other systems. Okay, so being able to be cognizant of what other systems can do and take advantage of those flexibly, and write your application in terms of these other systems that already do scale out, is a critical skill in data science. And so the point being made in this slide that is somewhat out of date, although you can get the idea, is that simple tools that are available on every machine, such as grep, which if you haven't heard of grep, if you're a Windows user and don't use grep too often, this is essentially search a file for a particular pattern. But it searches it linearly, right? It looks at every single line of the file and checks for the pattern. And so you can do a linear scan of a megabyte in maybe a second and a gigabyte in a minute and so on. And so at very large scale data sets, you can't do this linear scan anymore. You have to search in a smarter way. Okay, and you sort of have some costs over here that are probably horribly out of date now. All right, fine. So the point is, large scale data is not just bigger, it's different. It requires a different way of thinking about techniques, and it requires a different stack of technologies, and to ignore it's a mistake to ignore that in a data science course. Okay, and then this final dimension of sort of hackers versus analysts, and again what I mean here is, am I going to require sort of deep programming proficiency in order to participate in this data science class and in general in the data science kind of activities? And the answer is I don't think so. I think we need at least two types of people, and really sort of a broad spectrum of people. And this isn't really my idea. This often quoted report from the McKinsey Global Institute, you'll see this quote time and again. But the people that use this quote tend to focus on this first part that talks about 140,000 to 190,000 people with deep analytical skills. But the second part of the quote is, well, you also need 1.5 million managers and analysts who know how to use the analysis of big data to make effective decisions. Okay, so this means that it won't be just the programmers who are working in this space. And I wanted to sort of think about how to design a course that could appeal and inform both categories of people. All right, and this is my last side of this segment. The other reason why I think hackers versus analysts is that the line between them is kind of blurring nowadays, and technology can actually help here, right? It doesn't require a PhD in computer science or a bachelor's degree in computer science, even in some cases, to manipulate large data sets. And in order to back up this claim, I'll give you an example from some of my work where we have done some work to try to make databases easier to use for, say, biologists. And this really nasty looking SQL query that if you squint closely, you can see that it's actually doing interval arithmetic over genetic sequences, right? This is a pretty tough query to understand for even experts. This was written by somebody that doesn't do any programming whatsoever. She doesn't write a line of Python, she doesn't write a line of Perl, she doesn't write a line of R, and she's able to write these SQL queries that process very large data sets. Okay, so the fact that, if you understand what's going on and if you can think in terms of some of these abstractions and you understand your problem well enough, you can participate in the activity of manipulating large data sets and doing data science even without a deep background in software engineering. Okay, and that's why I want to push this needle somewhere over this way. I'd probably put this in the middle, I suppose. I'm not so much trying to focus on only the analysts. I just want to make sure that they're included. Okay. Next time we'll pick up with the last dimension.